Imagine looking up at the sky, breathing in the air, which is, mostly nitrogen, and thinking, that could be fuel. That could be food.
It's an amazing thought, right?
And it's really the promise that's driving so much of modern chemistry. How do we take that gas that's all around us and turn it into, well, the building blocks of civilization?
And we're really talking about ammonia here. It
Yeah.
is. I mean, it's completely essential for sustaining life on this planet. It's the basis for modern fertilizer, literally feeding billions of people.
But it's also becoming this critical carbon-free fuel source. You hear about it for, massive shipping fleets, heavy industry.
Yeah, it has huge potential, but there's a catch, a huge one.
It's the ultimate double-edged sword. Ammonia is life-giving, but the way we make it now is, frankly, an environmental disaster.
The current method is called the Haber Bosch process. It's over 100 years old, and it is an industrial behemoth. It needs insane amounts of heat and pressure.
And the carbon footprint is just staggering. It's responsible for about, 1.3% of global CO2 emissions?
That's the number. So if you think of Haber Bosch as this high-carbon, centralized giant of the past.
We need its renewable energy equivalent. We need a green solution.
Exactly. A way to make ammonia locally, just using electricity from solar or wind, all at room temperature.
Welcome to the Deep Dive. Today, we're taking a closer look at what might just be the biggest breakthrough in sustainable chemistry this decade.
Our mission is to unpack a really critical piece of research on how scientists are building an electrochemical system to make ammonia sustainably and, maybe most importantly, reliably.
Our source for this is a paper titled Stabilizing Calcium Nitride for Efficient Long-Term Electrochemical Ammonia Synthesis.
And this was published in the journal PNAS. It's from a team at the Department of Chemical Engineering at the University of Illinois, Chicago.
We definitely want to credit the authors here: Ishita Goyal, Hasia Najman Isa, Vamsi Vikram Gande, Rohit Chauhan, and Professor Manesh R. Singh. Their work is what we're digging into today.
And, the core problem they were trying to solve wasn't just making ammonia. People have done that in labs before. Right. The real challenge was stability. You can get a flash in success, a few minutes of production, but for this to actually be useful.
For it to be industrially relevant.
Exactly.
Yeah.
You need a system that runs efficiently, continuously, for days, for weeks, without falling apart.
Okay, so let's unpack this, and let's start where a lot of other researchers hit a brick wall, and that was with lithium.
Right. So the previous generation of these systems focused on what's called LiMA, or lithium-mediated ammonia synthesis. And on the surface, it looked kind of promising.
They had a proof of concept, at least.
Yeah, and some systems even got a high Faradaic efficiency, or FE.
Hold on, let's just quickly define that. Faradaic efficiency, for anyone who might be new to this.
Oh, absolutely. Think of it like the gas mileage you get from your electricity.
Okay.
When you put electrical energy into a reaction, you want as much of that energy as possible to go into making your product, in this case, ammonia.
And not into, say, making some useless byproduct.
Precisely. Fe is just the percentage of your electricity that does useful work.
Got it. So LiMAs had okay mileage, but you said it was flawed. What were the big deal breakers?
Well, there were three massive problems. First, lithium. It's not cheap. Second, the energy efficiency was just terrible.
Why was that?
Because lithium needs a really high electroplating potential. Something around negative 3.04 volts.
And what does that voltage mean in, practical terms?
It's a huge amount of electrical energy you have to pour into the system just to get the reaction started. I mean, just to get the lithium to deposit on the electrode.
So it's incredibly power hungry.
And expensive to run. And maybe the worst part, as you mentioned, was stability.
You said some of these systems were only stable for a few minutes.
That's what the sources say. Sometimes just 5 to 8 minutes at certain current densities, and then they would just collapse.
Yeah.
I mean, that's not a process. That's a failed experiment.
And there's one more problem that seems to plague all of these early attempts, right? Just getting the nitrogen gas to the reaction.
The mass transport challenge, yeah. Nitrogen gas, N2, is famously inert. It just does not want to dissolve in the electrolytes you need for this reaction.
It's like trying to get a fish to swim through molasses, you said.
Pretty much. The nitrogen can't get to the cathode fast enough to keep the reaction going at a high rate.
So lithium fails on cost, on energy, and on stability. So the UIC team Goyal, Singh, and their colleagues, they had to pivot, and this is where they bring in calcium.
Right, creating this new process they call CAMO-MS. And the reason for using calcium, Well, there were a bunch of reasons.
It starts with the basics, I assume. It's more abundant.
It's way more abundant than lithium and much cheaper. But the real chemical advantage, which theory had predicted, was better energy efficiency.
Because it doesn't need as much of an electrical push to get started.
Exactly. It has a significantly less reducing electroplating potential than lithium. It just requires less power.
So walk us through the chemistry. How does the calcium actually help make the ammonia?
It's still a mediated process, so you apply a current and calcium metal plates onto your cathode.
Okay.
That metallic calcium then reacts with the nitrogen gas that's dissolved in the electrolyte, and it forms this critical but very unstable intermediate.
And that is the calcium nitride, K3N2.
That's the one. The calcium nitride it's like the magic key.
Because it's super reactive.
Highly reactive. It instantly reacts with a proton donor in their system that's in alcohol, and that final step yields your product, ammonia, NH3.
So the entire process, the viability of it, hinges on being able to form and then stabilize that calcium nitride just long enough for that last reaction to happen.
That's the whole game. And that brings us back to that stability barrier. If the calcium nitride breaks down too fast, the whole system just fails.
And this is where Goyle and the team approach this not as a material problem, but as an engineering problem. They use three really smart design innovations.
Let's start with number one, solvent engineering. So the chemical environment itself. They saw that the commonly used solvent, THF, it just wasn't up to the task.
THF, that's tetrahydrofuran. What was wrong with it?
It just degrades. Under these harsh electrochemical conditions, it starts to polymerize.
It turns into goo, basically.
Basically, yeah, an electrochemical goo that just fouls up the electrodes and stops the reaction cold.
So they needed a solvent that could, handle the heat. And they swapped it for something called DME.
Dimethoxyethane.
Yep.
And this was a brilliant move for stability. It doesn't polymerize, so no goo. It's got a much higher boiling point, around 162 Celsius, which adds robustness.
And it does something special at the electrode surface, right?
It does. It forms what's called a stable solid electrolyte interface, or SEI.
Okay, that sounds super technical. How should we picture that SEI layer?
Think of it like a custom-fitted protector shield. It's like the outer armor on Iron Man, built right onto the surface of the calcium.
And with the old solvent, that shield was weak.
Porous and crumbly. But the DME helps build an SEI that's tight, stable, and protective. It stops all these unwanted side reactions that would just kill the process.
So chemical environment stabilized. Innovation number two was the hardware itself, the reactor. They found that the off-the-shelf cells were actually sabotaging their experiments.
Yes. The commercial setups, they had all these flaws, poor electrical contacts, gas flow was inefficient, the electrolyte would seep out.
There were just leaks waiting to happen. So the instability wasn't just chemical, it was mechanical.
Absolutely. So they designed their own. A custom continuous flow cell made out of a material called PEEK.
PEEK, polyether ether ketone. For our listeners, what's so special about it?
It's a super rigid, chemically inert polymer. And that inertness is key when you're dealing with these aggressive organic electrolytes.
So how does a custom PEEK reactor solve the problems that a glass cell couldn't?
The custom design let them perfect the gas flow. They stopped the electrolyte seepage, fixed gas crossover. It basically enhances that gas-liquid mass transport.
It forces more nitrogen into contact with the electrode.
You got it. Better hardware gives the chemistry a fighting chance.
Okay, so environment, housing. Now for the third innovation, the anode. This is where they make the protons for that final step, the hydrogen oxidation reaction, or HOR.
Right. They needed an anode that was efficient, stable, and this is critical, cheap enough to scale up.
So no precious metals if they can avoid it.
That's the goal. Initial tests actually showed that platinum-coated stainless steel worked best. It got them a Faradaic efficiency of around 9.5%.
Well, platinum is, it's the gold standard for a reason. It's incredibly expensive. You can't build a global industry on that.
No way. So they systematically tested other materials, and they landed on nickel foam, used for both the anode and the cathode.
Nickel foam. What makes that so special for this?
The foam structure gives it a huge surface area, which is great for reactions, and it's structurally very stable. But the key is, they proved it was better electrochemically using something called Toffel slope analysis.
And what does the Toffel slope tell you?
It basically measures how fast the reaction gets when you change the voltage. A lower number is better. It means the reaction's more efficient, the kinetics are faster.
And the nickel foam had the lowest number.
It did. It came in at 0.18 volts per decade.
Wait, what was the expensive platinum one again?
The platinum-coated mesh was 0.199. So that small sounding difference, it's actually a huge deal.
It's the technical proof of an economic win.
Exactly. It proves that the cheaper nickel foam has the fastest kinetics and the best efficiency for the hydrogen oxidation part of their system. It's the perfect combo of performance and price.
So we have the full package now: earth-abundant calcium, the stable DME solvent, the custom peak reactor, and the cheap NiFoam electrodes. Let's talk results. What did this combination actually achieve?
Well, the performance leap was it was huge. It totally validated their whole engineering approach. Remember that initial commercial setup? That only got them about 9.4% Faraday efficiency.
Right.
Once they moved to their optimized peak setup with the nickel foam, that peak FE jumped to an impressive 34.35%.
Wow. That's nearly a four-fold increase in efficiency. That's the difference between a science project and something that could actually be competitive.
But the truly game-changing number, the one that really signals this might be viable, is from the long-term stability test.
Okay.
Remember the 5 to 8 minute failures of the past systems?
I do.
The UIC team ran their system continuously for a stunning 56 hours.
56 hours, that's more than 2 full days, and it was stable the whole time.
Stable operation, maintaining a consistent ammonia selectivity of around 20% Fe, that's the difference between a lab curiosity and a real continuous manufacturing process. It's a breakthrough.
And they pushed it even harder, right, to test its industrial speed.
They did. They pushed it to a very high current density, negative 750 milliamps per square centimeter.
Which means you're forcing a ton of electricity through it really fast, kind of a stress test.
Precisely. And even at that stress level, the system held up. It achieved a really high ammonia partial current density of about 219 milliamps per square centimeter. The researchers said that's way beyond what previous studies have shown. It can run continuously, and it can run fast.
So the numbers are fantastic. But in chemistry, you have to prove your work right. The big question is always, where did the ammonia really come from? Was it just some contamination?
That's always the ghost you have to chase. So they used the gold standard for confirmation, isotope labeling.
They fed it heavy nitrogen.
Exactly. Instead of normal N2, they used N15. So the final product has a chemical fingerprint.
And when they looked for that fingerprint,
They found it. Using NMR spectroscopy, they saw the exact spectral signature they were looking for. And in their control experiments, when they used argon gas instead of nitrogen, zero ammonia.
so that's irrefutable proof. The nitrogen gas was the source.
It is. And they also confirmed that the critical intermediate, that calcium nitride, was really there.
How did they do that?
They watched it happen in real time using in situ Raman spectroscopy. They could see the chemical signature for C3N2 forming and, crucially, being stabilized. They even double-checked afterward with another technique, XPS, which confirmed calcium and nitrogen were on the electrode surface.
Okay, so if we step back and look at the whole picture, what are the key takeaways from this deep dive into the work by Goyal, Singh, and the UIC team?
I'd say first, this paper provides the real foundational proof for stable and efficient calcium-mediated ammonia synthesis. It moves it from just a theory into genuine engineering viability.
And second, the breakthrough wasn't one single thing. It wasn't a magic material. It was a holistic engineering approach.
Absolutely. It was the integration of those three key pieces: the DME solvent, the peak flow cell, and the nickel foam electrodes. It's a complete system solution.
And third, the numbers are finally credible for industry. Going from minutes of operation to 56 hours of continuous stability, that's what people have been waiting for.
That, plus the high-speed performance, makes this a serious contender to finally challenge the Haber Bosch process.
So this work really provides a clear blueprint for decentralized, sustainable green ammonia production. This is how you decouple making fertilizer and clean fuel from CO2 emissions.
And it opens the door to looking at other metals, too. The authors even mention it. You can look at magnesium, barium, strontium, sodium, other Earth-abundant metals that might work in a similar system.
Which leaves us with a final provocative thought for you to chew on. If this team succeeded by engineering stability around the calcium nitride intermediate, what's the biggest challenge going to be when they try this with, say, a sodium-based system?
Ooh, that's a good one. Because sodium nitride, Na3N, is known to be way less thermodynamically stable than calcium nitride.
So it's even more likely to fall apart.
It's the next great engineering puzzle, right? When the core chemistry is even less cooperative, how do you tweak the solvent, the reactor, the electrodes to hold that system together long enough to be useful?
A challenge for another deep dive, for sure. Thank you for joining us as we explored this really critical step toward green chemistry and a carbon-free future.
If you want to keep up with the breakthroughs that are changing our world, be sure to subscribe.